Hello everyone, I once again welcome you all to MSB lecture series on interpretative spectroscopy. In my previous lectures, about 8 lectures I gave focusing on UV visible spectroscopy, and of course I am giving more emphasis for inorganic molecules, in particular DD transitions. That means 3D, 4D, 5D metals having D1 to D10 electronic configuration show different type of absorption depending upon the nature of the ligands and also the nature of the metals and their oxidation state, and also under which ligand field they are situated. So based on all those things, lambda maximum varies, and also I showed you how we can simplify all electronic configurations, all metal complexes having different electronic configuration into simply 3 or 4 categories. One is D0 and D10. D0 do not have any electrons and D10 is completely filled. Unique cases, for example, you can consider potassium permanganate, potassium dichromate. In case of D10, you can consider mercuric iodide. And then the remaining ones, D5 is a unique one. Then the remaining 8 electronic configurations are D1, D4, D6 and D9, and then D2, D3, D7 and D8. And there is some similarities I showed you. For example, if you take D1, D4, D6 and D9, one electron is there and one less than half-filled electronic configuration and one more than half-filled electronic configuration, and then D9 is one less than completely filled electronic configuration. So these 4 electronic configurations, those metal complexes which have invariably show one DD transition, and then the second type is D2, D3, D7, D8. The similarities you can conclude in this manner: 2 electrons, 2 less than half filled, 2 more than half filled and 2 less than completely filled. So these show 3 bands in their DD spectra. And then of course D5, what happens when you look into selection rule, D5 high spin complexes have 5 electrons in T2G and EG in case of octahedral complexes, and in case of tetrahedral complexes we have here 2 and then 3 in T2 system. So in these cases what happens, since the selection rule says delta S equals 0 and delta L equals plus or minus 1, and strictly speaking none of these DD transitions should occur. They are all prohibited from Laporte rule. But what happens when we look into metal complexes, metal ions under the influence of ligand field, they lose the degeneracy of d orbitals, and some of the orbitals will be lower in energy, some of the orbitals in higher energy because of extensive mixing of d orbitals with s and p characters. As a result, what happens? They are no longer pure d in nature. As a result, Laporte-Allot transition could be seen, and hence we will see DD transitions. Okay. And selection rule, as I mentioned, delta S equals 0, and this is quite opposite to what we see in case of nuclear transitions. Nuclear transition, if you recall, is a delta S equals plus or minus 1. So that means a nucleus having spin half will go to spin minus half, downward spin. Whereas here, electron with upward spin should go like this only. So delta S equals 0 here. When you look into D5, they are spin forbidden, and especially when they have center of symmetry, the colors are very, very weak. But when we look into tetrahedral complexes, they do not have center of symmetry. As a result, some mixing is there, and hence we see some of these compounds having D5 electronic configuration with weak field ligands would be little colored. But why D5 octahedral complexes of having high spin still they color? What happens if we look into the ligands? Ligand to metal bonds are not rigid, but they will be vibrating with respect to the mean position. So because of these vibrations, at what happens, often some of these ligands come out of the equilibrium position. As a result, these complexes lose center of symmetry, and hence mixing would take place, and hence they show color. So this is all about UV visible spectroscopy. And again, for D1, D4, D6, D9, we can have conveniently one diagram that's called Argel diagram to explain electronic spectra for both octahedral and tetrahedral complexes. Similarly, we can have another one Argel diagram to explain spectra of octahedral and tetrahedral complexes having D2, D3, D7, D8 electronic configuration. But when you go to Tanube-Sugano diagram, every electronic configuration we should have a separate Tanube-Sugano diagram, but that includes the entire band of ligands. That means whether it's a weak field ligand, it's a high field ligand, everything is included. But we should have one Tanube-Sugano diagram per one electronic configuration. And also we saw in case of D2, D3, D7, D8, when there is a drop in the observed frequency of one of the bands or increase in there, because this is due to nephellaxetic effect, and that can be corrected using Racah parameters. And another important thing one should remember about UV visible spectroscopy is how to write term symbols. Okay, term symbols you should be able to write by simply knowing L, azimuthal quantum number sigma L, that gives capital L, and L can have anywhere between 0 to 1, 2, 3, 4, 5, and then corresponding terms we have SP, D, F, G, H, I, and then 2s plus 1 is called spin multiplicity, and then we have J, you can take values anywhere between L plus or minus S. And here what we should remember is when we identify the ground term, that should have highest multiplicity. When you look into highest multiplicity, maximum number of unpaired electrons will be there. So the one state which is having highest 2s plus 1 value will be the least energetic and ground state. And then due to some reason, if we have two terms both having the same multiplicity value 2s plus 1, then we have to consider the L value. Highest L value will be the least energetic. And then let us say we have multiplicity is same and then L value is same. In that case, we have to consider the J value. When you consider J value, we have to consider L minus S for subshells having less than half field electronic configuration, and then L plus S for those which are having more than half field electronic configuration. Then the other one is microstate. Microstate will give you ground state along with several possible excited states, and formula is very simple: n factorial over r factorial into n minus r factorial. So n factorial will tell you the total capacity of the subshell which we are considering. For example, if we consider d orbital, total capacity is 10 electrons, so hence n factorial means 10 factorial. If we consider f orbitals, we have 14 electron capacity, so it is 14 factorial. And then r is the total number of electrons we are considering, so d2 system, n factorial is 10 factorial and r is 2. So this is how you should be able to calculate the microstates, and all possible microstates are actually do not show transitions, and it is much simplified because we are bringing Laporte selection rule again, and hence it makes understanding and observed spectrum much simpler compared to what we could think of considering all possible microstates. So this is all about UV visible spectroscopy, and I would come back again at the end with more interesting problems to make you familiar with solving problems as far as UV visible spectroscopy is concerned. Now let's move on to IR spectroscopy. I am sure you are all familiar with infrared spectroscopy. So here infrared spectroscopy is a very important tool to chemists to identify what functional groups exist in unknown samples or samples we have made in the laboratory. The light our eyes see is but a small part of a broad spectrum of electromagnetic radiation in the visible region, I would say. On the immediate high energy side of the visible spectrum lies the ultraviolet, and on the lower energy side is the infrared. So you can see here we have visible spectrum here, and infrared is here, and microwave radiation comes here. So this is the region we are going to focus as far as infrared spectroscopy is concerned. So on the having a wavelength range of about 2500 to 16,000 nanometer, the infrared region is capable of revealing information not easily uncovered through basic means. So that gives vital information about different type of functional groups present, and also the characteristic bands due to the different bonds present in the molecule. The preferred method of infrared spectroscopy is FTIR, that means Fourier transform infrared spectroscopy, commonly used nowadays. IR can aid in the identification of unknown compounds, and also it can determine the quality or consistency of a sample if it is in the large production, industrial scale production. Then how it happens? When infrared radiation is passed through the sample, some of the radiation is absorbed by the sample and some of the radiation is passed through or transmitted. The resultant spectrum is nothing but the plot of percentage transmission versus frequency in centimeter inverse of the radiation that is passed through in the infrared region. So the energies of photons associated with the infrared region are not large enough to excite electrons, but they are still strong enough to induce vibrational excitation of covalently bonded atoms and groups. That means energy is of photons associated with infrared radiation is so small, it cannot really excite an electron from E1 level to E2 level, higher energy level, but on the other hand, they can induce vibration of the bonds. That means when we consider a molecule, we have covalent bonds. These covalent bonds are not rigid sticks or rods, but are more like stiff springs that can be rotated provided there is a single bond, and they can be stretched or they can be bent. So these different types of vibrational motions are characteristic to a molecule's component atoms. So this information comes directly from infrared spectroscopy. So all organic, inorganic compounds will absorb infrared radiation that corresponds in energy to these vibrations, and infrared spectrometers allow chemists to obtain absorption spectra of compounds that are a unique reflection of their molecular structure. So that means an IR spectrum can be considered as a molecular fingerprint of the sample, as no two unique molecular structures produce the same IR spectrum. So this is very, very important. It may not be possible to understand all the peaks present, and one need not have to worry about interpreting all the absorption peaks that are seen in that region. But what one should remember is this fingerprint region is characteristic of molecules. So what is the theory involved behind this infrared spectroscopy? So IR can provide information about the presence of particular functional groups, say whether OH group is there, whether CO group is there, whether amine group is there, or whether there is a C double bond, whether P double bond O or C triple bond N, C double bond N. All this vital information one can extract from simply by looking into IR spectrum of a given molecule. IR data along with NMR and mass spectrometric data can provide the structural features of a compound without any ambiguity. So minimum information about the theoretical aspects of IR is sufficient to use in structural analysis. So I am not going into the details of theoretical aspects, as I had mentioned, since my attention is to focus on interpretation with minimum theoretical background. I try to make you familiar with interpretation of data from various spectroscopic methods that we use routinely while characterizing organic or inorganic molecules. So IR absorption band of a compound indicate the presence of functional groups. This is the most important point one should remember. IR absorption bands of a compound indicate the different type of functional groups present in that molecule. So narrow and sharp bonds seen in the spectrum are called peaks. So peaks we call, our band positions are given in wave numbers as unit of reciprocal centimeter, that you know. In the IR spectrum, IR region between 400 to 4000 centimeter inverse is very important. Most of the functional groups have absorptions in this region of 400 to 4000 centimeter inverse. The frequency divided by C, the speed of light, provides the wave number. This one should remember. This indicates, for example, vibration of frequency 6 into 10 raised to 13 has a corresponding wave number 2000 centimeter minus 1, that's equal to, simply take 6 into 10 raised to 13 over velocity of light 3 into 10 raised to 10 centimeter per second. So that would give you about 2000 wave numbers. So this is how you can simply calculate the frequency to wave numbers. So band intensities are reported as follows. So by looking into the spectrum, we have to identify and we have to give a term depending upon the type of intensity we come across. For example, if it is strong, we have to denote it by S, and if it is medium, we have to say M, and if it is weak, we should say W, and if it is a sharp, we have to say sharp SH. a fundamental vibration is one in which an atom sets a simple harmonic oscillation about its equilibrium position. So, each atom, if you consider, has 3 degrees of motional freedom along 3 axes such as x, y and z directions. So, that means n atoms have 3n independent motions, but in a molecule the motions are not independent and motions within the molecule are not independent of each other due to having the bonds with the other atoms present in the molecule. So, as a result, 3 motions becomes translations of the molecule. So, where all atoms move simultaneously in the x, y and the z direction. So, another 3 are rotations where all atoms rotate in the same phase about the x, y and z axis. So, this is very important. So, all atoms move simultaneously in the x, y and z direction and all atoms rotate in the same phase about x, y and z axis. So, these points are very, very important, one should remember. So, this leaves now 3n minus 6 motions in which bond angles and bond distances without altering the center of gravity. That means it is 3n minus 5 motions for linear molecules. These are referred to as fundamental vibrations of the molecule and are of 2 types. One is stretching and one is bending. So, that imagine 2 diatomic molecule, 2 or 3 balls connected by a spring. If you consider a diatomic molecule, imagine 2 balls connected with a spring, or diatomic molecule, 3 atoms are connected with 2 springs. So, something like this. So, let us consider a triatomic molecule such as water, which contain 3 into 3 minus 6, 3 fundamental vibrations. What are those 3 fundamental vibrations? One is this one, symmetrical stretching, and then of course here the stretching frequency nu comes around 3652 centimeter minus 1, and then the second one is asymmetrical stretching, and here we refer this one as nu s, and here asymmetrical stretching is referred as nu as OH, or one can also say something like this. So, this indicates we are considering the asymmetrical stretching of OH group, and here we are considering the symmetric stretching of OH group, and asymmetric stretching value comes around 3756 centimeter minus 1. The other one is scissoring. So, focus towards scissoring. So, here this is again represented delta S here. So, delta S OH means it indicates the scissoring frequency corresponds to the OH molecule, OH group in water. This comes around 1596 centimeter minus 1. So, this is a typical example where you can see how 3n minus 6 equals 3 fundamental vibrations are seen. So, now let us consider a triatomic molecule which is linear. We consider triatomic molecules such as water bent. Of course, the shape is bent, still oxygen geometry is tetrahedral, but let us consider a triatomic molecule having linear geometry such as CO2. So, here if you use the same analogy, 3 into 3 minus 5 equals 4 fundamental vibrations are possible. So, what are those? Symmetrical stretching comes around 1340 centimeter minus 1, that is designated as nu s CO, and then asymmetrical stretching, again very similar to what we saw in case of water. So, you can see symmetric stretching, the directions given here, and in asymmetric stretching, so one is here, one is in this direction, other one is this one. So, this asymmetrical stretching is there, not uniform. This is also designated as nu as CO2. This comes around 2350 centimeter minus 1, and then we have scissoring bending. We have here it comes around 666 centimeter inverse and designated as delta S CO2, and then we have scissoring bending is there. So, you should know the difference, scissoring bending, this one scissoring bending, and here this comes around. So, both are identical. So, they come around 666 centimeter minus 1. So, this is how you can identify 4 fundamental vibration modes in case of triatomic linear molecules such as CO2. So, now let us consider a CH2 which is part of a molecule. For example, if you consider ethanol, propanol or any aliphatic molecules where we have CH2. So, in this case what we have is a 3n plus 6 rule does not apply here. Then we have to see what are the possible vibrational modes for CH2. So one is symmetrical stretching that you can see in most of the molecules around 2853 centimeter minus and designated as nu SCH2. And then similarly we have asymmetrical stretching. You should focus your attention also when I say symmetrical stretching, how these atoms are stretched in what direction. And then asymmetrical stretching. So one is in this direction, one is in this direction, one is in this direction. So this is called asymmetrical stretching, and here it comes around 2926 centimeter minus 1. And then scissoring, we have delta S equals 1465 centimeter minus 1. Apart from these three fundamental vibrational modes, we also come across wagging. So here wagging is referred to as gamma S. This comes in the range of 1350 to 1150 centimeter minus 1. And then another one is twisting. In the twisting, it's a stow AS, it is called as. Then this comes around 1350 to 1150 centimeter minus 1, and then the other one is rocking, both in the same direction. This is rho CH2, then that comes around 720 centimeter minus 1. So often the theoretical number of vibrations are not observed, and this may be due to symmetric reasons or due to degenerate vibrations. What is degenerate vibrations? Vibrations of the same frequency. So that means although we have clearly seen 6 possible vibrational modes for CH2 groups present in a molecule, sometimes we may see only 3 of them, and this is the theoretically predicted ones. But on the other hand, due to some reason that is clearly shown here, often the theoretical number of vibrations are not observed, and this may be due to symmetry reasons or due to degenerate vibrations. That means vibrations having the same frequency. In that case, we might miss 1 or 2, and then that might result in the increase in the intensity of few bands. So let me stop here and come back to you again in my next lecture, more details about infrared spectroscopy. So thank you so much.